Good morning to everybody, and a particular hello to the people that is following the session online. We have the honor of having Professor Yves Tillet for his master lesson. Yves Tillet is a statistician that works still in the field of sampling theory and methodology. He is Belgian, and really, he has devoted his career to the advancement of the field of statistics with the particular interest in balanced sampling, survey methodology, no-response treatment, calibration, and the development of sampling algorithms. He obtained his PhD in statistics at the Free University of Brussels, Belgium, before becoming a lecturer at the National School of Statistics and Information Analysis in Rennes, France, and then a professor at the University of Neuchâtel in Switzerland. His research contributed to the development of the cube method, a balanced sampling technique that ensures that the estimators of the total of selected samples are equal, or at least nearly equal, to the totals of the population variables. Throughout his career, Tillet has published numerous articles and books in peer-reviewed statistical journals. His work has also led to the creation of several algorithms and methods that are now widely adopted, especially in official statistics. The title of his master session is Data Science and Official Statistics. So allow me to remember another sentence, that is due to Sherlock Holmes. Data, data, and data. I can't make bricks without clays. It is in the adventure of the copper breeches. The copper breeches is only mentioned where something occurs. So if the floor is yours, and welcome to Professor Tillet.
Grazie mille. Sempre un piacere essere in Italia. Un giorno vorrei fare una conferenza in italiano. Peccato, la lingua ufficiale qui è l'inglese. So I have to speak about data science and official statistics. That's not at all a technical presentation. That's a little bit a presentation about philosophy of statistics. And first of all, that about the terminology, what is data science, official statistics? I believe that there is a lot of misunderstanding in the word we use, in fact. So you know that the word statistics comes from German, and that's proposed by an economist called Gottfried Achenwald a long time ago, because statistics was defined as a body of knowledge that a statement should possess. The knowledge needed to establish a good governance. And no, statistics is not at all that. That's a scientific discipline that studies phenomena by collecting, processing, analyzing, interpreting, modeling, and forecasting data, and not only a science for statement. And now we have this new terminology of data science. I believe that's a vague concept that encompasses statistics, information technology, computer science, database management, and mathematics. And that's not that clear at all when we speak about data science. So the first point, so I have big points like that, to say that statistics is a discipline that is not limited to state management. Here, obviously, we are in official statistics, so statistics is a discipline here that helps for the state management, but in general, that's not the case. And a very important development of statistics was done by Fisher. We was working in a station of agriculture, in fact. The word data is also very strange. In fact, data, that's a fact that is given or granted. And data is the plural of datum, and datum is the supine of a Latin verb de, meaning to give. You know that the supine is a modal form that exists in very few languages in Latin, that is between a verb and a noun, and that gives an intention, so that's intention to give something. In French, we have donné, that's feminine, and in Spanish, that's masculine. Why? And in Italian also, dati, masculine. In German, datum means a date. Data, in fact, datum. But I think that's a very bad term. Data is constructed following observation, experimentation of recovery from an administration procedure, and not only something that is given. That's not at all the problem. So I read in an interesting paper of Baker, who pointed out that the word data therefore refers to observation that are taken for granted, when in fact they never are. By always using the supine Latin verb, we could have taken capta to say that we have taken the observation, or collecta to say that we have collected the observation, or recepta, for that's the plural of the supine to receive, that we receive the observation, or obtenta, that the plural of the Latin obtinere, to say that we have obtained the observation. In fact, the word data was invented firstly in astronomy, in fact, a very long time ago, so that the data of the sky, that's something that is given in the sky, probably by God. And that's why this word data was used, so that given that what you can observe, that's the data that's given. But the statistician's task is not only to process data, in fact, that's to produce data, that to obtain data, that's to correct data, and try to deal with measurement error. That's a big deal. And the data, in fact, are not given. And so that's also a very big misunderstanding in the terminology of statistics. And so the word data obliterates the heaviest and probably most important part of the statistician's job. It contributes to the myth, and this myth is very important now, that the data on anything and everything is available at any time on the internet, for instance. And this myth is more relevant than ever. A lot of people believe that, okay, a part of the production of the Statistical Institute can be replaced by a machine that will produce automatically things on the internet. And with the development of the internet, there is a tendency to state that all statistic information will be easily and directly available. And that's a modern myth, and that's confusing with this word data, in fact, that is given. Now, a little bit of history. You know that the Belgian statistician, okay, Quetelet, Adolphe Quetelet, he was Belgian. No, not really, in fact, because Belgium is a little bit an error of history. And it was Spanish, Belgium was Spanish, and next Austrian, and next invaded by France at the French Revolution. And next, it was a joint country with Netherlands, and the independence of Belgium is in 1830. So he had 4 successive nationalities, Adolphe Quetelet. And the predominant idea in the 19th century is that we need exhaustive census to produce reliable information. That was, in fact, the dogma or the paradigm of the 19th century. So if you go to Quetelet, that was written in French. Quetelet was from the University of Ghent in Flanders, but the University of Ghent was teaching in French during the occupation of Netherlands. That's a little bit strange, huh? So she said that Laplace has proposed to substitute, you know, this story, for the census of a large country such as France, some special census in selected department where this kind of operation may have more chances of success, and then to carefully determine the ratio of the population either at the birth and the death, because you can have the list of the birth in the church, in fact, but not the list of the population, so that's given accurately. By means of this ratio of the birth and the death of all the other department, figures can be ascertained with sufficient accuracy. It is then easy to determine the population of the whole kingdom. This way, that's important, this way of operating is very expeditious, but it supposes an invariable ratio passing from one department to another. This indirect method must be avoided as much as possible, although it may be useful in some cases where the administration would have to proceed quickly. It can also be used with advantages as a means of control. In fact, that's not true. That's not Laplace who used at the first time the ratio estimator. There is a paper of Ken Brewer in 2013 who wrote the beginning of the paper. No, Laplace had not been the first person to use a ratio estimator, not even the first Frenchman. There is the Englishman John Grote at used a ratio estimator in his estimation of the population of London before Laplace. Well, perhaps he had not really used the ratio estimator. He probably hadn't used anything that would be recognized as a ratio estimator today, certainly not by finicky survey statistician like me, but he admitted to use the rule of three. The rule of three. It's important to see the argument of Ketley to justify this position, because that's dogmatic, in fact. To not obtain the faculty of verifying the documents that are collected is to fail in one of the principal rules of science. Statistics is valuable only by its accuracy. Without this essential quality, it becomes null, dangerous even, since it leads to error. And next, there is the famous scandal of the Norwegian statistician Anders Nicolas Kjær, who proposed the first time in Bern, in fact, in a meeting of the International Statistical Institute. He proposed the use of a partial data produced by survey sampling, and that produced a very big scandal. If you read, that's very strange, but all was written in French during this period. I translated it. The representative, it was the director of the Statistical Institute, Georg von Meyer, that said it is especially dangerous to call for this system of representative investigation within an assembly of statisticians. It is understandable that for legislative or administrative purposes such limited enumeration may be useful, but then it must be remembered that it can never replace complete statistical observation. It is all the more necessary to support this point that there is among us in this day a current, that's very nice, a current among mathematicians who in many directions will rather calculate than observe. So you can see the presentations now in statistics, we can rather calculate than observe. But we must remain firm and say no calculation with observation can be done. And there is the representative of Switzerland, Guillaume Millet, that say, I believe that is not right to give a congressional voice to the representative method, which can only be an expedient. No doubt, statistics made with this method, or as I may call it, statistics part pro toto, part for all, has given us here and their interesting information, but its principle is so much in contradiction with the demand of the statistical method that as statisticians, we should not grant to imperfect things the same right of bourgeoisie. So that's a very nice, the right of bourgeoisie, in French, the droit de bourgeoisie, so to speak, that we accord to this ideal that scientifically we propose to reach. So they rejected this method completely. And next, you know the story. It was only after 30 years that the idea of sampling was finally accepted by the International Statistical Institute. They created a committee with a lot of well-known persons, and there is this report of Jensen, where directly they accept the idea of using a sample, and directly they did the difference between purposive selection of the sample and random selection of the sample. And now, to go fastly, with the development of computers, administrative files were created and began to be used as statistical sources. Say, 50 years ago, some countries had a register of the population and can use this register to produce statistics. And now the accumulation of data on the internet is intriguing. The volume is enormous, and the question is whether this data can be put to good use, but real applications, I think, are still extremely rare. And now we are in the world of sampling, and in official statistics, the main objective when you select a sample is the extrapolation of the data that's a bad word you have collected, you have received from, maybe from God, is the extrapolation to a population. Now, from the internet, we have a wealth of information that is available. In general, this information cannot be extrapolated to the population as a whole. And I believe that the main problem is not the quality of the variable, that's the definition of what is the unit of observation. And so we need to have a clear definition of what is the unit of observation. And sometimes the notion of unit of observation is not very clear. Notion like establishment, for instance, or household are not simple. Even in Switzerland, there is a different interpretation from one canton to another one of what is, in fact, an household. And the extrapolation from the internet is not often not possible because of the definition of what is the unit of observation. Now, we know that in general, the framework is that we have a variable y, still that's the same. That is the variable of interest, and we have an auxiliary variable, that x, that is known or partially known. So, in fact, if we do calibration, we only have to know the total or sometimes less. So we have x that is partially known and y. And the aim is like that. We select a sample, and the sample is not selected to be for itself, to be extrapolated to the population. And that's the main problem, that's to find the principle of extrapolation. And so as principle of extrapolation, we have the two big approach. We have the design-based approach here on the left side, again, the model-based approach. So in the design-based approach, we suppose that we know the inclusion probability, and if we know the inclusion probability, that means that we have selected the sample from somewhere so that we add, at least at the moment, add the list to select the sample, and so we know something about the population. And in the model-based approach, we try to predict the units that are not selected in the sample. That means that we use a model, but that this model must be applied of units that are not in the sample to have a forecasting for this unit. So in the two cases, we need an auxiliary variable. We need something from the population, and we need auxiliary information. And next, this auxiliary information can be used at two stages. The first stage is to use it at the sampling design to select a good sample, for instance, a stratified design or to balanced design with equal or unequal inclusion probabilities. Sometimes there are good reason to select the units with unequal inclusion probability. And next we can use the auxiliary information at the estimation stage to correct non-response, to do calibration, or to have something that is more efficient. But we can say that to extrapolate, we need information from outside of the sample. So that's very important. We cannot only use the sample to do the extrapolation. We need a principle, and we need something from outside of the sample. The inclusion probabilities, in fact, must be computed for all the population to select the sample. So we need something from outside of the sample to do extrapolation. Now, to extrapolate, we have a multitude of methods: weighting, mass imputation, modeling, prediction, propensity score methods, calibration. And all these methods, the aim is to graft an extrapolation principle onto data that cannot be necessarily extrapolated a priori. And for most methods, extrapolation can be formalized by a weighting system. Even if you do mass imputation, you can count the number of times a unit is imputed, and you can do a weight by using that. And okay, that's the mission of official statistics, to provide a framework for extrapolation, as the information needed to apply the principle of extrapolation cannot be produced by the data without structure. So that's the next point. In official statistics, most methods aims to re-establish extrapolation. Even we have seen in data from the internet, we try to graft an extrapolation principle onto the data. Now I will speak a little bit about errors. Errors are not necessarily a big problem. The fact that estimates contain error can be more or less problematic. Errors do not contaminate all estimators in the same way, and the people in official statistics know that very well. So suppose that we have two estimators of the same parameter at two different times, to hat 1 and to hat 2, and they have error. Yeah, and that we would like to compute the increase. The increase, for instance, we would like to compute the increase of inflation or increase of GDP. If there is a big error in the first and in the second estimator, but if they are very correlated, in fact, the impact on the increase will be very small. And the people know that in official statistics. If you want to have to change the production to compute inflation in another way, the big problem is that you will have a gap. And maybe before we had more important error, but the evolution is consistent. That's like a thermometer. They do that in meteorology. If you change the thermometer, maybe you have the gap. In meteorology, you continue using the L thermometer in 2 years in order to calibrate the data. We could do the same in official statistics, but that's impossible, too expensive to use the former way of measuring things during 2 years with the new way. So an error in the data is not necessarily a problem for an estimator, and that's an important point. Another point is this term representative. You know that I don't like this word, but this word was already used by Anders Nicolas-Kiaer. In fact, he used a quota method, and that was not very good because he used a systematic sampling on the first letter of the names of the people, and you have a bias with that. If you take the names, the family name beginning by W in Belgium, yeah, you will have probably more Dutch-speaking people than French-speaking people. So the method was not very fine. So the method representative is a very bad term because the journalists in general believe that in order to extrapolate the sample would be a sort of reduced image of the population, that in some categories the proportion should be the same in the categories, in the sample and in the population. And that's not true, in fact, because 1 century ago, Cassie, Jerzy Neyman will show that we have a big advantage of overrepresenting the observation of the most dispersed category. And we can obtain much more precise estimates than in a supposedly representative sample. And now that's used completely in establishment survey. And this idea was generalized. Now, if you have a linear model, you can, if you assume before selecting the sample that you have a linear model, it is possible to show that in this case, if you compute the anticipated variance, the anticipated variance is the variance under the sampling design and under the model, you can show that the best design is a balanced sampling design on the independent variable of the model, and you have to select the sample with unequal inclusion probabilities proportional to the standard deviation of the error terms of the model. And a special case of that is the optimal stratification of Neyman. So the use of word representativeness is an argument from authority. You must be careful about that, which shows above all that the person using this word doesn't know much about sampling theory. So avoid that in general. Now, I can speak a little bit of the use of unstructured partial data set. That's a very fashionable topic now. There are people working in the papers from Yang and Kim and Tam, Kim, Wu, Valiant, Jocelyn Thier, that's a PhD student of me. We did matching system. Chen, Wang, and Beaumont. Beaumont has written a very nice paper. That's a comment on a paper in survey methodology. And he did a very nice conference, Jean-François Beaumont, in Esch-sur-Alzette in Luxembourg, in the French-speaking conference on survey sampling. But above all, so we have unstructured partial data set, and always the idea is to graft an extrapolation principle onto the unstructured data set using another sample with an extrapolation principle. Now, there are questions about the definition of the variables. There are questions about the definition of the statistical units, because the extrapolation principle is not a question of variables, it's a question of the definition of the units and to extrapolate to the complete population, to the set of units to the population. So the notion of the variables, that's also be confusing. So for instance, if you speak about the disposable income, you have a booklet like that of Eurostat to define that. And that's difficult to avoid ambiguity, especially where there are pensions, for instance. In some country, you can take a part of your pension in cash or not, and that's a mess if you speak about disposable income. And there will always be a room for interpretation. And moreover, a variable is measured at a particular date, in a particular territory, in a particular population. And for this reason, we know that there is never a perfect match, even between a well-organized and up-to-date administrative file. We have never to believe that we will find the perfect match of the definition, technical definition of a variable in an administrative file. So the administrative files also contain errors. And the errors are not the same that the errors we have when we produce the variable ourselves. Because in official statistics, the variables are produced for statistical purpose. There are often marked of non-response, but fairly standardized procedure make it possible to deal with this kind of problem. Administrative data can have problems of quality and lack of updating because they are produced for administrative purpose. If a variable is not really used for an administrative point of view, it may be completely neglected. So, for instance, if we have a well-maintained housing register and a well-maintained population register, we can make many errors concerning the allocation of the individuals to using in the same building. I speak about that because we had the problem in Switzerland, the definition of what is an household. So Switzerland is a country that is very decentralized. And there is only one canton where there is no trash tax. But the trash tax is a tax on the household. So if you want to put a trash tax, you need a good definition of the household. If not, you have a problem. And in fact, each 3 months, the cantons, there is a population register, has to give to the Swiss Federal Statistical Office a copy of the register of the canton. And in the canton where there is no trash tax, there are problems in the definition of the household. So you have an address, and you have 3 children of 10 years in the same household, and 3 persons with the same name as the children in another household, because they don't need it. They don't need it because that's not related. There are no use. So in the same address, they mix it. They mix the people like that. But if you send the trash tax, that's related to the number of inhabitants. If there is an error, the people will contest directly. So, but the fact that some variables are poor quality is not necessarily serious. If this problem, if you want to calculate the average size of household, you don't need to know which household each individual belongs to. You just number the number of households and the number of people to do the ratio. If there is a problem to do that, there is no necessarily a big impact. Now, another problem of error that is very interesting is when you have error in your auxiliary variables. You know the theory of Deville and Sarndal. We calculate a weight for each individual K in the sample, and we would like to estimate the total Y of a variable of interest using an estimator on the sample S that use weights, and the weights are calibrated on the variable xk. It does not matter whether the X variable contains error or not. The only important thing is that they are correlated with YK. If there are errors, that's not a problem. Only the correlation is important. So error will not introduce a particular bias in the problem. So you can use a variable that is full of errors to do calibration. Because but you have to calibrate the errors on the errors. That means that you have selected the sample using the register with the error. And after that, you don't have correct your register with the information coming from the sample. Because you have to use the same variable to calibrate on the right side here and on the left side. So you have to conserve the error and calibrate the errors on the errors. So an error filter variable can be used if it contains an extrapolation principle, because X is used to have an extrapolation principle and not used for the quality of the measurement. And if there is an extrapolation principle, even if there are errors, we can use it to do calibration. So we can use variables where we have a lot of errors. But errors must be calibrated to errors. We have to calibrate on the same variable. We don't have to correct one and try to correct the other one, and next we calibrate a thing on another thing. Now, about massive and non-organized data. It is illusory to think that the massive non-organized data in stream or social network can be valued. I am convinced of that. I am still waiting real application. Okay, there are some. There are some in price index, people looking the price of the plane tickets and things like that. Okay, it can work. Because there are problems with the required quality. It is not possible to determine the population from which the statistical units originate, not the reference dates, and the statistical units cannot be matched with no statistical units. There is no extrapolation principle on the internet to reconstruct estimator at the population level. What's more, the internet is not stable over time. That will change maybe very rapidly. Maybe Google will disappear and we will have only ChatGPT. And simply tracking the price of a product over time is far from straightforward. And despite all the fuss about big data in official statistics, applications remain anecdotal. There are applications. It's clear that in Switzerland, the statistical office use photo of the territory to produce the statistics of the territory. That's a very hot topic because there are very few ground for agriculture, and so they try to evaluate the reduction of the ground in function of the building. That's a very hot topic. We vote a lot of time about this topic. And so to do a good production statistic of the territory is very important. Now the definition of machine learning. Did you ever look to Wikipedia? What is machine learning? That's a field to study artificial intelligence concerned with the development and study of statistical algorithms that can learn from data and generalize to insert data, and this perform tasks without explicit instruction. Recently, artificial neural networks have been able to surpass many previous approaches in performance. Okay, that's true. And in the article, you can find a list. Probability calculus. Okay, it was invented by Laplace. No, Gauss. Regression, you have regression. Regression is machine learning. Cluster analysis, logistic and regression, principal component analysis, fuzzy logic, and neural network. You use fuzzy logic? No. PCA, principal component analysis, was proposed by Pearson in 1901. So that's a new method of machine learning. And you can also see compression algorithms, numerical analysis, operational research. And if you read this site, you see that the definition is confused. The machine learning methods are not necessarily modern, and that a large proportion of machine learning methods are recycled classical statistical methods. So we have now a change in terminology this change of terminology is intended to make people believe that there has been a break in statistical methods. I believe that's not really true. And we could even use the grandiloquent term of paradigm shift, but I believe that's not true. Method concerning sparsity for high-dimensional data are old. So the lasso was published in 1996 by Rob Tibshirani. And the last century in the rich regression were proposed in 1970 by Hall and Kenner, more than 50 years ago. Neural networks also existed for several decades. So in neural network, it's clear that there is an improvement now. So I will not contest that. And random forest, when produced by Breyman yeah, a quarter of century ago already. So statistical, so that's my big ideas in big characters. Statistical learning is the new version of statistics in which not so new statistical methods have been recycled. Now, another word about the crisis of statistics. You know that this is the crisis of the p-value, and that the crisis of the p-value that is very discussed now. So it remains a very important argument if you see in biology, for instance, in medical science. And there is this question about arcing, because that's ugly. But that means hypothesis after the results are known. So you take your file, you do a lot of p-value, and next you take the p-value that are less than 5%, and you construct a theory about that, and you publish that as it was a theory you had at the beginning before producing the data. And so now there is a lot of questions about that. And some people say that most of the scientific publications are false because people are always doing things like that, trying some p-values and conserving only the part. And next, there is a second step where the only paper published are the paper that are significative. And so there is a second step of selection of the paper that increase the number of false positive in science. And now you can see that if you open a journal of statistics, a journal of modern journals, there are very few p-values in the journal of statistics. There are very few things about test theory. But and it's clear that in a discipline that's a very important impact. And it's surprising to see how many scientific disciplines base their argument essentially on hypothesis testing, while there are very few references to the test theory in the new publication in statistical journal. And even if test theory seems a little bit outdated, no, especially when we have a lot of data, it still remains a master argument in science. Another question is the progress in the forecasting method that we can use in official statistics. So we have new forecasting methods, so like random forest, that working very well. So for instance, to do imputation, you can use the method of Peter Bullman of the University of Zurich that is called Miss Forest. So imputation by random forest. So we can do very accurate forecasting, but it's difficult to really explain the relationship between the predicted variables and the auxiliary variables. And in official statistics, the final objective is often not to make a forecast, but to extrapolate to the population. However, all high-performance forecasting methods can be useful. A prediction can be considered as a value of the variable of interest containing error. So if we have a variable and principle of extrapolation, we can use it. Insofar, all the values of population can be predicted. That predicted values provide a framework for extrapolation to the population. That's an idea that is the subject to numerous publications now, especially Dagdug and Aziza, Kim and Tam, Yang and Kim. So any prediction can be useful, even if the model can't be really explained, provided that the prediction comply with an extrapolation principle. Now we have another problem, the loss of confidence in official statistics. The response rates are failing in surveys, political pressure, the contest is mounting to reduce the statistical burden, especially for business survey. In Switzerland, there are a very strong pressure of professional organization, and it's difficult to ask again for information that has already been requested. Even in Switzerland, that's in the law. If the state knows the information, you cannot ask the information. But what is the information? In fact, the variable is changing with time, and that's not up to date. There are still problems. But you cannot ask a question that you are supposed to know. But that's not the case. So I filled the form for my pension, so they ask a lot of information they are supposed to know. In fact, that's completely stupid. So in addition, concern about data protection are becoming increasingly important. And I would like to say something about that. Statistical institutes are among the most close scrutinized government bodies, because that's easy. This may seem odd because we, the statisticians, we are not interested in people or companies, but in parameters or average, totals, inequality indexes. However, statistics are easy prey when it comes to data protection, because if you have a committee for data protection, so it's easier to impose roles to a statistical institute than to a secret service or to the police force. And so that's an easy prey. Official statistics are therefore in a delicate position. There is an urgent need to make the most of all alternative sources to survey and census, and difficulties are compounded by the fact that data seems to be available everywhere and all the time. And so this is this fantasy of immediacy of knowing everything about everything. This fantasy of everything can be found on the internet sometimes leads to the idea that official statistics can only be obtained from the internet. But in fact, if you look for, you want to have the fertility rate of China, you look on the internet, but finally, the number is produced by the Statistical Institute of China and not by the internet. So they just take, use something that is produced by the institute. And that's obviously a myth that we can produce from the internet. There are relatively few alternative sources that can be extrapolated to the population of interest in official statistics. Added to this is the fact that the government IT environment are often lagging behind and ever obsolete. I can speak about that because we were active at the University of Neuchâtel, and the university had to reformat all the computers of the university. We were completely paralyzed during two months. And the fragility of the system in the face of hacking does not make the job any easier. I can tell you that in the Swiss Statistical Office, that's very well protected. You need a card, a lot of things, but there is a firewall. It's impossible to download the air package. You have to ask an authorization to download. Next, you have to develop, new methods. But you have to ask the authorization to download the air package. So the main challenge now is to make the most of all administrative data. However, the data is often of poor quality because it has not been collected for statistical purpose. A major challenge is to harmonize data from different sources, and the battle is far from won. Administrative sources are sometimes delivered with considerable delay. We have the problem in Switzerland with the pension system, because the first pension system in Switzerland, that's federal. So they have an information for all the people working, so all the people are included. They know exactly in which situation is each person, but you can have the data only 2 or 3 years ago. So you can say, oh, the employment increased a little bit, but 3 years ago. That's not very interesting. The statistical units sometimes do not correspond between the statistical concept, for instance, of establishment or taxable legal entity, or between the statistical concept of the household and the taxable family entity. And many countries, even in Europe, are unable to find out who lives where in the country and how many citizens are in which municipality. And countries that do have registers sometimes find it difficult to use them, particularly when they are decentralized, like in Switzerland. So that's a big challenge. I believe that the reconciliation of sources, that can be an headache involving a considerable amount of work that has to be repeated every year. And there is such thing as immediate access to information. It's also difficult to recruit skilled workers in the data science field of IT and statistics, and private companies often pay better for qualified people. States' inflexible pay scales do not allow high qualification to be considered. A solution can be to outsource the methodology. And for me, that's the worst error we can do. That can seem like an emergency solution, but outsourcing your core business in management is always a very bad idea. In highly technical field, it is often the case that administrative and political leaders are unable of understanding the work to be done and the real issue at stake. That's a fact. You chief don't understand what you are doing. So that's the case in a university, but that's normal. You know that the rector don't understand what you are doing if you are doing in Spanish literature, for instance. And now there is a fact that's very annoying. That's this guruism we can have. There are people, that are no guru that can have significant development of improvised expert with good communication skills, taking contacts with politics, and this phenomenon of guruism generates an additional fog that makes it even more difficult to make informed decisions. You can see a lot on LinkedIn. Gurus are easy to recognize. They use slides with potatoes and arrows. So that's if you have slides with potatoes and arrows, that's a guru. Only buzzword, like a list of words beginning by V. You have seen that. That's completely silly. That's like children. You do a list of animals beginning by C. Now they do a list of words beginning by V, and you are a guru. And so to see there are lotto like that, you can do a bingo. You have sheet like that, you go to the meeting, and the first one who found all the best won the meeting. So the challenge is that we have to have a best view of administrative data. There is a lot of preliminary work to be done. Administrative databases are rarely perfect. If the data is not used for administrative purpose, that's rarely reliable. The variable definition can vary. Slightly different definition can constitute an household or a business can be emerging file inextricable. The problem of temporality is very important. Business move, die, burn like individuals, and more they split the families. However, the main problem seems to be of legal nature. In fact, there are a lot of problems to obtain the administrative data. There is a legal problem. And in Switzerland, there are a lot of conflicts between the federal state and the cantons. And the compartmentalization of administrative service, the complicated relations between states and local authorities, the data protection legislation sometimes may seem administrative use very complicated. Access sometimes require legislative change that can take a long time because that have to pass through the parliament. And another challenge is the integration of sources. Hundreds of publications have been devoted to this issue. However, However, there is no clearly defined methodology. Each case is a little bit unique. It depends. Methods as diverse are calibration, small area estimation, statistical matching, and massive imputation can be used. Everything obviously depends on the data available, on the existence of identifiers enabling matching, and the use of data from the internet will probably remain very anecdotal. I predict that, so that's the only thing I predict. Maybe I am doing a mistake. There are applications. I told you satellite aerial photos can be of very, very good quality. But with that, if you have photos, in fact, you have a principle of extrapolation. That's not like the data of the internet, because you have all the territory. You have directly the principle of extrapolation. And making the most of this data will require statistical institute to master new image analysis technology. Another problem are the error. Public statistics is always a fight against error, correcting, reweighting. So we have a big specialist here, David, David, of error imputation techniques and to resolve problems of non-response and calibration techniques. So the statistician know more or less how to deal with measurement error, but each data set is unique. If you want to model the non-response, that's not the same from one sample to another one. And there is also no universal principle in this area. In addition, a new statistical method of prediction need to be tested and integrated. They are likely to bring considerable improvement. The fourth challenge is technological innovation. So the statistical methods are developing very rapidly. So we have 100 statistical journal, maybe, 100. Maybe if there is 100 article in a journal, maybe that's a lot, 100. There are 10,000 articles each year in statistics. But I believe that the problem is important, and I argue in favor of developing teaching and research in statistics and in official statistics. So the scientific research is very, very important. It will make possible to tackle questions that will arise in the future and that we do not yet know. So I explained that when you teach statistics, it's not to teach topic, it's to be able to read a new book. That's the aim when you teach something, because the statistic will be completely different in 10 years. So the most important thing is that the students are able to continue learning. And so the Statistical Institute needs a strategy to develop research and scientific activity. So outsourcing your core business, your main activity, statistical methodology, means losing your soul. And that's all. Thank you very much for your attention.
Thank you very much, Professor Tille, for your stimulating conference. And I think that now we have room for not question, but I think for opening a discussion, because the topics you raised are really of general interest. I'm sure that many amongst us have a lot of things to say.
Hi, yes. I think you gave representativity a bad name. So representativity has nothing to do with proportional allocation, right? Because in indicators, we use design weights. And it's basically how it reflects the achieved sample and how it reflects the original sample, which of course indirectly relates to the population. But the issue is you can't talk about representativeness without talking about the auxiliary variables, right? It has to be in the same breath, similar to, I suppose, balanced sampling, right? On what are you balancing? And so I think that representativeness always has to be specified in terms of representativeness, in terms of what variables.
Yes, thank you for your remark. So my presentation was a little bit provocative. Now, I remember a paper, I have to search a little bit, where there is a list of the different definition of representativeness. And there are at least 10, you see. Some is that some categories in the same proportion. So that's, in general, if you speak to a journalist, they believe that. Eh? They don't understand that you need a property in the sample. But that's not that the problem. We are statisticians. The properties are for the estimators. The sample is only a tool. So the sample can be completely different from the population and very efficient to construct because the property is unbiased. Some people say the sample is biased. But yes, but a sample cannot be biased. But people say that if there are null inclusion probabilities, so the sample is biased. But in fact, that's not the definition of an unbiased estimator. So there are at least 10 different, you can say, okay, there are no null first order inclusion probabilities or no null first and second order inclusion probability because you should be able to estimate the variance. Or, you can see that there are, and so I believe that clearly there is a misunderstanding. If you use this word, okay, if you are a statistician, that's related to that you have an extrapolation principle. But extrapolation principle is that, okay, you have non-null inclusion probability, so you can extrapolate. In this case, you can do something that is unbiased or quasi-unbiased. So, but okay, my remark was a little bit provocative. So I believe that the terminology is not clear, in fact, not clear at all, and that we must avoid to use this word. That's all.
A consideration about your definition of machine learning as not a complete novelty with respect to the models that are in this new approach. There are a lot of them, linear models, logistic models, and so on, that are by far introduced in our environment. But in my opinion, the novelty of this machine learning approach is in the fact that you can cope with the problem of the trade-off between bias and variance by introducing the difference between train and test sets, and by choosing the most fit model by considering a lot of them with the same approach. I mean, when I was a young student, I remember that there was the linear model, and you have just to fit in the given data set and use that, something like that. Now it is much different.
I took the definition that I found on Wikipedia, in fact. So you can see the website. But that's clear that there is something very different now. So I believe there are two big uses of statistics. There is a lot of people, for instance, in social science, are doing an analytic approach. They want to say if there is a relation between this variable and these variables. So they use a test theory. They say, oh, I discover something very important because the social categories are related to this behavior and this, that. So this is the analytic approach of statistics that is based on the test theory. Now, Next, you have another point of view. You have, for instance, in finance, you would like to predict. The way of predicting is not very important. You want to win money. So you want to have a good forecasting. And so you can completely change the way, the approach to construct a model, not to have an analysis of the situation, but to have a forecasting that is efficient. And so that's clear that's the approach we have in the new method. So because, for instance, in the lasso method, we evaluate the quality not by test, by doing cross-validation. So we try to see if the forecasting is good, if the forecasting is correct or not. And in that, there is a change because we select the variables not in function of an analytic analysis. In fact, we are not really interested if the variables are related or not. We can just ask the question, are the variables useful to do good forecasting? Maybe there is a relation. And we know that if we increase the size of the population, of the sample, all will be significant at a certain moment. But maybe this variable is not useful to do a good forecasting. And that's the idea of the lasso. And in this sense, there is a change in the methodology that is pushed by the fact that now we can have a lot of variables. You see in biology, the people, they have a machine, they put things in the machine, and the machine will test if there are genes, DNA, and they compute directly 10,000 genes if they are present in the liquid. And finally, they have a table with 10,000 variables and only 100 of observation. What can you do with that? Eh? You have to use methods that are completely different. But that I completely agree with your remark. Eh?
Thank you. I found the lesson very, very interesting and intriguing because you took it back to the fundamentals. My main idea that remained after your lesson is the principle of, come si dice? The principle of
Extrapolation.
The extrapolation. This is fundamental. And I think that with this principle, we must keep, as of official statistician, that this principle must be seen joined with the errors that in the extrapolation we can make. And so this principle is linked to the principle of errors and give some information on errors.
Yes. Yes, there is the problem of errors with the extrapolation. But sometimes we can, important point is that you can have auxiliary variables with a lot of errors, and that's not a problem.
Giving some ideas to the users that does extrapolation we make may be subject to errors, give some measure of possible errors. So, because to give to computer statistics is easy, but to give a measure of uncertainty of that measure may be, and that I think that as official statistician we should take care of this.
Yes, I completely agree. And moreover, there is Ray Chambers, who is, I believe, very clever, told me once that in statistics there is the principle of Heisenberg of statistics. That means that if you want to have a very accurate sampling design, for instance, stratified sampling design, the most accurate is to put only one unit by stratum, to select only one unit by stratum. But in this case, you cannot estimate the variance. And so there is a kind of contradiction between having a very accurate estimator and a very accurate estimator of the variance. That's in most of the case, that's contradictory. So you should relax a little bit. So people say, okay, you need only maybe 10 units in each stratum to estimate the variance. And between the estimations, what is the most important? I believe that's still an open question.
Thank you, Yves. So going back to your previous comment, I think maybe this is just naive, but the comment you made before is when you discuss calibration and say, even if X has errors, as long as X is a good predictor is correlated with Y, then you have a better extrapolation. And I think that machine learning is essentially the same, but it's just like moving away from a linear relationship with Y. So anything that is something that can help in the extrapolation, even if it's non-linear, it just allows that to be non-linear, very complicated whatsoever. And that's why you move away from p-values and you just need some cross-validation to make a good prediction.
I completely agree. Because I completely agree with machine learning. You have a forecasting, and you can consider that the forecasting is a variable, maybe with error. And next you do like the publication of that Dagdugan-Aziza, you can use a difference estimator to have something that remains unbiased under the sampling, more or less unbiased under sampling design. Yeah, I completely agree.
Yeah, and the and as of the use of internet data that will just remain anecdotal in the future. Two comments. First, 25 years ago, when I started with the machine learning things, I think it was believed to be similar. I mean, using machine learning in survey sampling sounded as incredible as using internet data now. I think now, after 25 years, it's very much in practice. But so I do believe that there are instances in which it is useful. You mentioned GIS data. We saw MNO data yesterday, so the cell phone data to try to estimate commuters. So there might be instances in which it is useful. But I really found interesting when you said that one of the main issues is like what Li Chun would call entity ambiguity. So the fact that the unit of internet data can be really different from the unit we are interested. So I was wondering whether it would be enough if you find a link between those units and the units you are interested. I was just wondering whether you need all that, or maybe you need something less to make it useful. I don't know.
Yeah, I think that if you see that's the problem. You need an extrapolation principle for the units. Maybe for the phone, you have a list of the phone numbers in the company. Sometimes you have a list. So the problem in most of the cases to graft an extrapolation principle on your data to do something, because the problem is to extrapolate in all the cases.
In the light of your consideration, how do you think we should change the PhD program for the new era statistician, or whatever we want to call them?
In general, my opinion is that we have to, is that teaching must not be a catalog of holidays. Don't do a list of methods rapidly. We have to see the things in detail, regression in detail with all the things, with all the theorems. Because the competence is not what you have learned, but what you will be able to learn. That's like that. So the topic is not very important. The problem is that if I give a book to the student, what do I have to teach in order that the student will be able to read this book after that? But in Switzerland, in statistics, in the French-speaking part of Switzerland, we have a very nice program, or PhD program in the Alps. We have a meeting twice each year, and we invite very known persons. And so it's important also to have a general culture, a little bit in statistics. But this doctoral school remains very technical, in fact. Very technical. We have to see, the content a little bit deeply for PhD students.
Yeah, thanks, Yves, for your slightly provocative presentation. I would like to add something to the anecdotal reference that you can use big data. There are 6 successful applications, so it's not anecdotal. But the interesting thing is, I could discuss them individually, but the interesting thing is, in all those cases, the phenomenon you're measuring is directly related to something that you can collect from the internet. And if you have a population in which you can couple, for instance, web pages from companies, if you can link that to the business register, then you can easily produce a reliable statistic based on that. So there are some organizations that are quite ahead of that. So it's possible to do that. And one of the obvious things is, if you are interested in producing a consumer price index, then you only need the prices of products. You can easily collect them from the internet. So there's no difficulty there. So I hope you get my point.
I didn't understand very well your question.
Oh, no, I'm just adding information to the fact that you said that there are only anecdotes on which you can successfully use data from the internet to produce official statistics. Yeah. So it's there. You just need to look at the correct papers to do that. And if somebody is presenting giving a presentation on big data and mentioning the 10 V's or the 6 V's, yeah, that's outdated. So that you're entirely correct regarding that point.
Yeah, on business survey, I believe there is a use of this idea of establishment, so that's very difficult to establish a link, in fact, of the unit, the definition of the units. Now, I also think that in official statistics, the situation can be very different in different countries. There are countries where there are very beautiful population register, for instance, and with that you can do a lot of things. You can do a lot of matching with register of very good quality in Netherlands, for instance, or in Belgium, Finland, or in all the Scandinavian countries. And so, yeah, there are countries where there are links between the files. So I see, you can see directly. I was in different countries living, and in Belgium, yeah, that's very different from Switzerland and France. In fact, there are 2, 3, and you see that in Belgium, all is linked. In fact, there is the register, but they know all about you, and all is linked. And you have an ID with a puck and a pin, and you connect. You can see all the papers you assign in the administration. But with that, if they use that in official statistics in Belgium, there is no census for 30 years, and there are a lot of information. Very nice thing. You can see how the people are moving from which municipality to each one, and next there are open situations to do matching with that. For the extrapolation, there is something that is very clear, in fact, if you have such a register.
Thank you.
Yeah, thanks. I enjoyed your presentation. I'd like to add something to the discussion that Giovanni started. She asked about whether it's the best a link between the units in your big data set and the units in your target population. I think it's not really necessary. If you aggregate everything to the level of your publication domains, you can do some modeling there and use the information from your big data set as auxiliary information. So I think you can relax that.
Yeah, you can have, that's the case in calibration. In calibration, you need only the total. Yeah, so that's why I said you have a partial known of something on the population, you can use it. But that should be relay, that should be the total of the same variable, that the one you have in the sample, because something is coming from a census. Is it the same data, the same definition of the variable? But yeah, that's the case. If you have a sample you calibrate, you need only the total. That's already an information.
Yes, okay. First of all, I'd like to thank my colleague. I'd like to thank you for the presentation, but I'd like to thank my colleague Massimiliano Spina, who works in the library here in Istat, because he was able to find out the old books by Ketele. And so if anyone wants to see them and to just look at what Ketele used to say, you can find that. I'm going to ask you a question for which I am a bit afraid. Not of a question, I'm afraid about your answer. And because, one of the main issues that as national statistical institutes we are performing in the last years relates to the use of data from internet or big data and consequently, probably the biggest effort right now is the definition of a quality framework for the use of such data in official statistics context. So I wonder what could be your advice on how to establish this kind of frameworks, according to the ideas you presented here. For instance, one of the biggest efforts is about representativeness. So I wonder if you have any kind of advice for the people that are building these quality frameworks in national statistical institutes for the use of such sources.
My advice is clear, is for an institute of official statistics is to do research, in fact, to have relation with university or to have a department of research. There are several possibilities, but we are in a very technical domain, and we need to be up to date. We need to do research. We need to do teaching, to have links with universities, maybe to have agreement of university. And it's important also to do basic research, not only things that are very applied, but to have questions that must be developed during several years. And that's important, and to maintain a link between the universities and the statistical office. So that's my advice.
Thank you to everybody. Thanks to Professor Tile. Are further intervention from the floor? Well, if not, we are perfect in timing. The session is closed and the coffee break is ready for us.
Thank you.
Okay, let's see if people can start to settle down for the session. So for this session we have two invited talks. Okay, I mean, you know both, so I don't need to say too much. The first speaker will be Professor Pierluigi Conti. So if you are ready, please.
Okay. Good morning. Before starting, let me thank the organizers for their kind invitation, and in particular Mauro Scanu. Well, this talk is essentially related to integrate data coming from a probability sample to data coming from a non-probability sample. And let's start with the problem. Probability sampling. Probability sampling usually consists in a non-informative sampling design, which is constructed on the basis of design variables. Each population possesses a known positive probability of being included into the sample. And if the population have different inclusion probability, there is, broadly speaking, selection bias. However, since inclusion probabilities are known, we can compensate for the selection bias simply by weighting with a possible gain in efficiency, namely in reducing the variance. This is the well-known inverse probability weighting principle, but it can be expanded through modifications of the weights. For instance, we have learned this morning through calibration or other. Okay, post-stratification, which is a form of calibration, etc. Non-probability samples, well, they involve a degree of arbitrariness in the selection process of units, and inclusion probabilities are usually unknown. From now on, I will mean by non-probability samples, samples where the probability of selection units is unknown, essentially, and uncontrolled, basically. Okay. Unfortunately, in this case, it is not generally possible to remove selection bias through weighting, because inclusion probabilities are unknown. And even more unfortunately, very frequently the selection process is selective with respect to the target population, in the sense that inclusion probabilities may depend on the character of interest. This is really a bad news. As a consequence, estimated constructed through non-probability samples may be strongly biased. This is well known. Everything up to here is well known, but now the question is, how could we quantify how biased is a sample? Or better, since biasedness and unbiasedness refers to estimator, how an estimator, to which extent an estimator is biased? Could we bound its bias? Okay, let's analyze this in a very simple case and under certain hypotheses. Let me introduce first symbols. Consider a finite population of size n, say UN, and let A and B be two independent samples. The first one, A, is a probability sample drawn according to a non-informative sampling design. B is instead a non-probability sample drawn by some unknown, say, probability selection process, say. Let me denote by Y the target variable, the study variable, which takes value yi over unit ui, and let x be a set of auxiliary variables taking values xi over units. Okay? Well, the peculiarity is that in the probability sample A, the controlled sample, say, only values xi's are observed in sample A, but in the non-probability sample B, both xi's and yi, the target value, are observed. So potentially, sample B provides information on the character of interest. Well, let me denote by di the sample membership indicator of unit I, say, from sample A, and let pi A be its first order inclusion probability. Let further delta I be the sample membership indicator for unit I from sample B, namely delta I is equal to 1 for units into B, belonging to B, and delta I is 0 for units outside of the non-probability sample B. And let me denote by Pn the joint population probability mass function of y and x. Okay, and further by Pn of y, Pn of y conditional on x, I will denote the mass function, I call probability, but they actually are frequency mass function at a finite population level. I will introduce a further layer of randomness, say, consisting in a superpopulation model, where P of yx is the superpopulation joint probability of y and x, pi of y is the marginal at a superpopulation model level of y, etc., etc. Okay? Well, how to use data coming from the non-probability sample B, let me stress again, containing both y and x, to estimate the probabilities of interest, namely the marginal of y and possibly the conditional of y given x. Okay, the basic, apart a few recent approaches, I learned actually some of them yesterday, there are two basic ideas. The first one consists in estimating in some way weights for the non-probability sample. Hey, after all, it's a natural idea. Let's try to weight the observations in the non-probability sample by estimating weights through the parallel probability sample. The second idea is fairly simple as well, consists, let's impute the missing y values in the probability sample B. A, okay? And in both cases, Professor Kim, among the other, gave several fundamental contributions, but both methods work under an essential condition, namely the selection mechanism from the non-probability sample is again ignorable, namely the probability of including a unit into the sample B conditionally on covariates axis doesn't depend on y. So let me stress again conditionally on x. Okay? Okay, let me introduce, well, in order to quantify the potential bias due to the non-probability sample and the selection process mainly related to the non-probability sample, let me introduce a few further symbols. Let me denote by, and hypothesis as well. Let me denote by delta I, yi, xi, the triples consisting of sample membership indicator for non-probability sample, y value and x value for non-probability for the whole population. And my assumption is that the random variables xi and yi are jointly IID at a population level. Further, I will assume that y is a discrete random variable. This is just for simplification. It's not so crucial, but anyway, let me just assume the variable of interest is discrete, categorical, say taking capital J categories. Let me further assume this is, in a sense, more delicate. The covariates axes are discrete, taking H categories. For instance, this occurs in stratification, post-strata, etc., but also in other cases. But the main example are, of course, post-strata. And the crucial assumption, similar to Kim, Wang, and others, is that the delta I's, the sample membership indicators for probability, for the non-probability sample B, are also observed in the probability sample A. Okay, this assumption will be used. Okay, the main quantities of interest are the joint, say at a superpopulation level, but the same can be done at a finite population. So the symbols are more complicated. So I will focus on the superpopulation level just for the sake of simplicity. Let me denote by Pyx the joint of y and x, and P of y given x the marginal. And since the marginal of x can be actually consistently estimated and identified by our data coming from the probability sample A, the problem of estimating the joint and the marginal of y can be reduced to the problem of estimating this conditional of y given x. Okay? So, well, how, well, and now let's focus on what we can do and what we cannot do. Well, first of all, let me remark that the conditional of y given x can be written in this form, can be decomposed in this form. And the part is probability of including a unit in the sample, in the non-probability sample, conditional x times this conditional probability of y given x and inclusion of a unit into the non-probability sample. It is a sample distribution according to Danny-Pfefferman, plus the same thing for the non-included units into the sample. And this is the sample complement distribution. And here they are specified through the bias theorem, say. Okay, it's just what Danny-Pfefferman showed yesterday. That's essentially the same consideration. Okay. Well, there is a big difference between these two guys. The first one is identifiable on the basis of our sample data, or better, on the basis of our sample process for non-probability sample. The second guy is not identifiable at all. The problems come from the sample complement distribution. Okay, so the probability of including a unit into the sample into the non-probability sample is actually, on the basis of the assumptions I made, is identifiable and estimable. I use maybe a little bit naively as a synonym. They are not synonym, but everything which is identifiable can be actually estimated. Stay consistently and possibly asymptotically unbiased. Well, the first term, this inclusion probability, can be estimated from sample A, but the probability of not including units into the sample, into the non-probability sample, cannot. Well, it can be estimated as well, sorry, again on the basis of sample A. What cannot be identified and estimated as well is this quantity here, namely the sample complement distribution of the character of interest, which is essential if we want to reconstruct this conditional here, and the joint and the margin as well. Okay, so I have just two remarks. What is the role of ignorability widely used in this kind of analysis? Well, the role of ignorability is relatively simple, because if the sample process, the sample design, say very broadly speaking, selecting B, the non-probability sample, is ignorable, then this guy here and this guy here do coincide. And then I have no indeterminacy at all. If we don't assume ignorability, instead of identifying a single probability distribution for y given x, we identify a whole class, which can be written in this form. Namely, it's a mixture of sample and sample complement distributions. And gamma ranges over this class here. And this quantifies exactly, enucleates in a sense, the role of the unknown selection process of the non-probability sample. Okay, so whenever the a non-probability sample is selected according to some process which depends on Y and X as well, we can't identify this probability, conditional probability, and we have a whole class of probability distributions. In a sense, this is related to the selection mechanism of the non-probability sample, which decides, in a sense, using the language by Meng, the level of resolution of our data. Through our data, we can identify this class, but we can't single out a distribution within. So, what is the final effect? It's uncertainty on the conditional probability of Y given X. And uncertainty is completely due to the selection mechanism that generated the non-probability sample. The larger the class of plausible, the larger the class gamma, namely the larger the class of plausible sampling designs selecting the non-probability sample, the larger this class H. And the problem is how to measure uncertainty on this class. Well, the simple idea is to evaluate this uncertainty through the sides of the class H. Let me, this is constructed to a contingency table where a column, this first one, is essentially unknown, whilst the second column can be actually estimated through sample data, and also this row, the last row can be estimated as well. And so the basic inequality, according to this, is that the probability of category yi given X ranges in between this quantity here that can be estimated on the basis of sample data, and this quantity here that can be estimated as well. So instead of having a single estimate, or better, instead of having a single value, the level of resolution of our data only enucleates a range, an interval, for a single conditional probability. Okay, as a measure of uncertainty, the most natural idea is to take the sides of this interval, which is, let me denote by capital U, the measure of uncertainty in this case. And so the measure of uncertainty is simply equal to this quantity here. We know. Let me note in passing that it is uniform with respect to YR, YJ, the category, which is, say, a feature. Okay. Parallel to this, measures of uncertainty for the whole distribution of Y given X and the marginal can be introduced. Okay. What is the most interesting feature? The most interesting feature is that the uncertainty measure introduced so far can be actually estimated on the basis of sample data, coming from both sample A and sample B, coming from both the probability sample and the non-probability sample. So we can have an idea of how uncertain we are about the probability distribution of Y given X. Because we have a range of estimates, we can't go into the range. Well, we can, but we are uncertain. And but we can estimate the whole range, say consistently. And parallel to this, we can propose estimators of the uncertainty measure, and the estimators are, as usual, under appropriate hypothesis, consistent, asymptotically normal, etc. We can even test if the uncertainty is below a certain level or above. Okay, but this is not well. And now there are two further points to be discussed. The first one is that sometimes extra sample information are available. For instance, we could say, hey, but suppose we have, suppose Y denotes classes of income. Observed through a non-probability sample. Of course, people that say the probability of not responding, the probability of not revealing income is the highest actually for small incomes and large incomes, okay? So we know that, for instance, the probability of having a certain income for respondents can be smaller or higher than the marginal. So this is an auxiliary information, rather reasonable, and can be included into the evaluation of the uncertainty. Well, in the extended paper, we have considered essentially two kinds of auxiliary information actually interacting each other. The first one is that condition is in the form of inequalities. Like I said, probability of observing a category Yj conditionally of having included a unit into the sample is smaller than the corresponding, or larger, that's the same, of course, of the corresponding marginal. Okay? For some categories. Other kind of auxiliary information can be included into the sample are preliminary estimates or say shorter ranges for conditional probabilities or other. Okay, preliminary estimates provided by experts, etc. Well, and this kind of information strongly reduce, can be strongly reduce the uncertainty in the sense that it can be reduced, it can be made our uncertainty intervals tighter, smaller. And in this sense, the total uncertainty is reduced. In this case, what we usually obtain are bounds that are not uniform with respect to the category, but this is not necessarily a bad feature. For me, it's positive. Okay, again, under the same irregularities conditions as before, estimates of bounds are consistent, asymptotically normal, can be tested, etc. Okay. Now, my final, how much time do I have? 5. Okay. My final considerations are about estimation error and the role the uncertainty measure introduced play on the estimation error. Well, let me denote by, let Uj, Lnj be the upper lower bound for the probability of Yj conditional on X, and let U hat and L hat be their sample estimates. Okay? Each probability in between this lower bound and this upper bound, it's a legitimate estimate of the actual conditional probability of Y given X, of the true probability. And under wide regularity conditions, each estimate we can construct within that interval, I should say each bona fide estimate of the conditional probability I can produce under, say, fairly general regularity condition, it does converge to a certain point in the interval, in the true interval containing the unknown conditional probability. Unfortunately, the point at the probability, the conditional probability at which we have convergence is not equal, not necessarily equal to the true conditional probability. So we have indeterminacy. Indeterminacy is due to the unknown selection process for sample B, again. Well, what about the estimation error? The estimation error can be decomposed into these terms. Estimator minus quantity at which it converges plus second term, which is essentially a bias term. And this bias is irreducible. In terms of mean squared error, the total mean squared error can be decomposed into the sum of two components, variance, squared bias, and they have a completely different behavior. The variance typically does tend to zero as both sample sizes tend to infinity and the population size as well, okay. The second term, no. The second term typically remains positive. And however, something can be said, because the second term is bounded by our uncertainty measure. So we can provide an upper bound for the bias. Let me just add a few things. First of all, this bias term here is intrinsic to our estimation process. It's a form of indeterminacy, like the Heisenberg indeterminacy principle, but it is not related to variance as the true Heisenberg principle, but to bias. The result is simply bias. Simply, it's bias. This bias is bounded. We can provide a bound. We have also a minimax estimate, which is the midpoint of the indeterminacy interval, but this is just a minimax solution, nothing special. And what is important is that although the bias remains, its upper bound can be estimated through sample data. So we can at least have an idea of how uncertain we are and what is the effect of our, say, non-probability sample on the precision of the estimates we can produce. Of course, further developments are necessary. First of all, same theory, say, but for a quantitative character Y. Secondly, I assume that delta, the sample membership indicator for units are for units in the non-probability sample are observed into the probability sample. Sometimes this is not possible, but it could be possible. For instance, use techniques such as record linkage. But as said by Lichung, this produces virtual units and a further source of error that has to be quantified as well. Okay. Probably it's an additional term. Then we should also introduce the possibility, which is real, of non-responses into the probability sample, which is another source of error, possibly additive with respect to the others. So there is much work to do. This is just a first step. Thank you for your attention.
Thank you very much. Now I invite the second speaker. No, we do the presentation, I do the discussion, then we open for the floor. Okay. So our second speaker is Professor Brunero Riseo.
Hello. Thanks the organizer for suggesting me to speak about this relatively new topic for me. And I want to start with a disclaimer. I'm not here to sell conformal prediction, just we wanted to explore the potential benefit of this relatively new methodology in survey sampling. And this is what we did. So the overview is very quick. What is conformal prediction and how can it be used in design-based or model-based survey sampling? And then if there is time, I will speak about some possible agreement between Bayes and frequencies model-based analysis. So let me start with a very simple and general framework. We have a imagine a regression analysis, nonlinear regression analysis. So we have a sample of observation. The variable of interest is y, and then we have some covariance xi. And those observations are, for the moment, independent. And we want to estimate a regression. So our estimate is f hat. And then after doing this step, we want to build a prediction interval for a new observation, y, about which we know the value of x. So we want to make a prediction interval, c of xn plus 1, which is the f hat evaluated at x plus some delta. And our goal is that this interval should have a coverage guarantee. So the probability that that interval will contain the value of y should be at least 1 minus alpha. This is the problem. Of course, we all know that would be incorrect to use the training residuals to build the interval, because the training residual have already shown the data, and the estimator is built on those data. So using that kind of residual, you will have some overfitting of your estimate. So what is the alternative idea proposed by the conformal methodology? I will introduce only the split conformal, which is not the full conformal because of a matter of time. And so this is the much more popular used. So you split your data half and half, and you use the first half of your data and use those data to fit your regression function. F hat now has a n over 2 here. Then you consider the other half of your data and compute the residual using the second part of your data. Then you order your residual and consider the residual, the rank of those set of residual located at the position ceiling of 1 minus alpha and half. So a quantile of the bag of the residual. And then you can make a prediction by taking the point estimate evaluated at x n plus 1, the new observation, where f is computed on the first half of your data, plus or minus the value of the quantile. So in this case, and this is crucial in the theoretical development of conformal prediction, all the computed residuals now are exchangeable, because the second half didn't see the first half, and so the new point is exchangeable with the second half of the point. There is a theorem behind this proposal. If we assume that the pairs xi, yi are exchangeable together with the next one at the n plus 1, then the probability that the new value is included in the prediction set is at least 1 minus alpha, and this result holds for any finite sample size. So this is a great result. There is no asymptotic argument here. For any fixed n, you have the guarantee that the coverage is at least 1 minus alpha, and in many cases with continuous variable, you may make this result more precise. And the proof is not so complicated. It's based on the notion of popular notion among statisticians, like quantized permutation and exchangeability. So basically, the intuition is that the prediction set will consist of all the points y, such that y is not so far from the f hat evaluated. Sorry, it should be n over 2 here, and the threshold k will depend on the conformity score, the residual that I mentioned before. So it will be a sort of quantile of the distribution, of the sampling distribution, the sample distribution of the quantile. Let me repeat what I said with formula with picture. Imagine that we have this data. This is the entire set of data. Then you half the data. Half of them are training, half of them are calibration. So now I consider only the trained data. I estimate my regression function this way. Then I eliminate the calibration, the training data. I use the calibration data, and I compute and I compare the calibration data with my fitted line, and I compute the residuals for each of these points. I make I order this residual and compute the quantile among those residuals. And then I take new data. This is my test data. So it's a third data set. It's the one for which I need to make prediction. And what I get by using my split conformal prediction, you will see that only in this picture, 5% of the points will be outside the band that I constructed using the second part of the data as my calibration set. So this is how conformal works. So let's see how can we use it in this context in official statistics. So this is my setup. It's very general. So we have a finite population of size n. We know the membership whether each single unit is in the population or in the sample or not. We assume that we know the covariance for all the observation, but we only see the y for the observation in the sample. So we have our data consists of xj, yj, when j belongs to the sample, and then we know the configuration of the sample. So in general, we assume that there is a big probability distribution P involving the ij, the membership, xj, and yj. Okay, I can imagine that this distribution is pi times the conditional distribution of x and y given I. So we have found only one paper dealing with conformal inference in conformal prediction in design-based. It's a paper by Via Cesare. It just published in the survey methodology, and it made some simple exercise in using conformal prediction in very simple design-based setup. And what can we say is that it's very easy to handle in simple random sample, because in that case, you may assume that the observations are exchangeable, and it requires some ad hoc correction with more general sample scheme. But I will say more on this later, hopefully. So notice that here the probability distribution is over I, over the design. In a model-based context, the goal is different. You want to be calibrate with respect to the distribution of x and y. And our idea, the result of our simulation tell that the conformal can provide some advantages in terms of mitigation of the misspecification problem, which is one of the reasons why most people doesn't want to use model-based in survey sampling, can produce narrower prediction interval. And for the moment, let me skip the base frequencies idea. So we know that it's always very difficult to ask data to Istat. So we decided to use some publicly available data. There's a big data set called EpiPop in the R package survey. It consists of 6,000 schools, and for each of these schools, we know a lot of variables, 25 variables, and we only consider as our response the academic performance index, which is a number between 200 and 1,000, and then a set of auxiliary variables. One is categorical, the type of school, and some other are numerical. the percentage of English language learners, the percentage of students eligible for something. We don't care much about it, just an example. So let's look at the result. We have compared several different methods of estimating the mean of yi. The first one is of course, oh, sorry, I didn't say that this is a simple, we run several simple random sampling. So this is the performance of design based with sample size 200 at the alpha equal 0.2. Okay, so this is the coverage distribution of the 80%. This is the model based with one covariance, using one of the three X. This is a model based with two covariants. This is a model based with three covariants. This is the design based conformalized, okay, using the conformalized methodology in order to correct the coverage. And again, with the same color, you see the other method based on the model based. The last one is the bootstrap. The one in the middle is the full conformal prediction. The full conformal prediction, in theory, is much better than the split conformal prediction, but it takes a lot of computational time. So in practice, it can be used, but it should be our benchmark to maximize the potential of the method. This is the same with at level 95%. So alpha is 0.05 now, and you see they are quite different in behavior. I mean the non-conformalized methods. Now we can see over coverage for the design base and for the model with just one covariance, and we need more covariance to reach the correct coverage. And this problem is not present in the conformalized version because one of the main brick is that we are going to have exact coverage. But this is only half of the story, because the other half deals with the length, the expected length of the interval, and this is what we obtain. Again, 80% of coverage, sample size 200, and you see that these are the same interval as before. But now there is a big. Now you can appreciate the difference between conformal and bootstrap, because the bootstrap will provide much larger interval, and of course the best one is the model based with three covariants, and because we are using a lot of information here, and the model was quite correct, let's say, so the interval will be much narrower than the other. But in any case, the expected length of the interval is not larger than the others. Let me say something about it. This is independent of our experiment. Of course, the success of the conformal prediction methodology is related to the coverage. The length of the interval will depend on the statistical method that we have used in the step one, of course. Better method will provide better interval, of course. Narrower interval. Okay, this is the other simulation with at 95%. So first comment that we are able to make. Design-based conformal versus linearization. Yesterday we have seen a paper on linearization, and there is a common author in the two papers, so she wanted to make this comparison. And in the final sample guarantee and the fact that the method is model-free is an advantage of conformal prediction when compared to linearization.
and versus bootstrap on other resampling methods, the best pros is the fact that the coverage is finite sample, which is quite important. And also, from the computational perspective, split conformance is much less intensive with respect to general resampling method. This is not true for the full conformal prediction, which is even worse than a bootstrap. In the model-based, of course, as I already said, the combination of conformal and the correct model of course provide the optimal interval, and there is some work in this direction already published in the Journal of Survey Statistics and Methodology by Peter Hoff and collaborators about small area estimation. And this is, in that case, they are able to find the optimal interval for predicting value at any small domain using this strategy. The other byproduct is that if you use a poor model, then it will cause an increase in the length of the interval, but does not undermine the coverage, which can be important. Okay. There are challenges. I have 5 minutes. Thank you. There are a lot of challenges, but if I'm probably I will be able to speak about this the first 2 points. I don't speak about classification because classification is a strange problem, because when you want to predict something and your variable is discrete, then this set are set of points in a sense, and they deserve a different methodology, always still based on the conformal idea. And then point D was suggested by Marco Dizione in a discussion. Sometimes we can make a prediction at a very micro level by, for example, predicting the probability that an individual belongs to a population. And so we have a conformal prediction for each single individual. How can we sum up together those intervals? There is no theory on that. We have some preliminary result, but we have no still a consolidated theory. But let me speak about the first 2 problems: conditional coverage and adaptivity. Of course, there are some value of X where I have more information and some value of X where I have less information. So I don't want to have a marginal coverage like the one that I showed before, because somewhere I can be more precise. And so what should be obtained is that the probability of Y given conditional on X, so we would like to have a conditional coverage conditional on X. And this is not, in general, this is not possible to obtain. There is a general result. This is a paper on Series B 2014. And if you have a continuous X, there are no non-parametric methods that can attain conditional coverage for any value of X. However, we can do something, of course, and there are 2 ideas. The simplest one, of course, is to studentize your residual, your conformity score. Of course, if you have an estimate of your volatility of sigma of X, then you can studentize the residual and use them when you build your confidence interval. This is the easiest one. There is another idea which is a little bit more complex, because in this case we abandon the idea of the point estimate in the middle, but we only consider the 2 different quantiles of the first part of our data set, and this is called the conformalized quantile regression. It's a paper by Romano and Manuel Candes, and which works better than the studentization of the residual. This is just an example with the data that I showed you before. That was the interval that I showed at the beginning, the constant band around the point estimate. This is the studentized conformalized interval, and this is the conformal prediction made based on quantile, where you don't see you never see the internal point estimate. The other problem, which is quite important in survey sampling, is that in survey sampling, exchangeability never occurs. So this is the main thing, because sampling design are more complex, and so what is imagine that you want to predict the value of new observation, and this new observation doesn't come from the sampling design that we have used before. So in that case, there is the main solution to this problem. There's a lot of research in this field, but the main idea is that is what is called the covariance shift. So in a sense, we assume, and this is an hypothesis, that the only difference comes into the distribution of the covariance X. So you assume that Pi is the same, Py given X is the same, but Px is different for the observation that doesn't belong to the sample. Okay, because this new observation comes because of a new design, a new sample. And then this problem can be solved simply by weighting the conformal score that we have created before, and the weight will be given by the likelihood ratio of the two measured P star and P, the two Px and P star X that you see here. You simply weight the conformal score of your points by taking this W of X, the ratio of the two probabilities, and then your Bayes residual will not consist of R1, Rn as before, but now you have R1, Rn weighted with this P, and the P are the relative weights of the half of n points in the calibration set plus the new points, the one where you want to make the prediction, the star point. Final, yes, just wonderful. Just 1 minute for one slide, and an interesting point related to conformal is the fact that one of the main criticisms regarding the use of model-based technique is the potential dependence of your answer to the model. And if the model is not well specified, your conclusion can be biased. And even worse, if you do Bayes, then the introduction of prior information can even more jeopardize the unbiasedness of your inference. However, if you use even an hierarchical Bayes methodology with your prior information, whatever you want to use, and then you introduce as a conformal measure, not more the residual like I showed you before, but the posterior predictive density of your Bayesian model, then you will get conformalized interval with the correct guarantee. And this is what is masterly explained in this paper, in recent paper in survey statistics and methodology, with an application in smaller estimation using an hierarchical Bayes approach. So in a sense, it could be a way of harmonizing different approach to getting the correct result coming from different routes. Thank you. Thank you. Thank you for two interesting talk. I think I will go. My discussion will go the sequence. Let me time myself. Okay. So the first paper, essentially, it is about the uncertainty due to what we might call the unknown selection mechanism. To briefly recap, we observe delta and x jointly. We observe y given x and delta equal to 1, but we do not observe y given x when delta is equal to 0. But the distribution function of y given x and delta equal to 0 can be rearranged so that you see the red term. That's essentially the thing that is unknown here, that is causing trouble. However, we cannot sort of point-wise identify this, but we can bound this. So, for example, if we sum over all the y's, everything in the bracket, then you get essentially 1 minus all the probability of delta equal to 0 given x. And from this, you lead on to the conditional measure given x and marginal measure integrated over the marginal distribution of x. So the intuition is very simple, right? Very clear. I don't think anybody can disagree. So essentially, so imagine like this, given x, the probability, the total probability mass for which we don't observe y, we cannot point-wise identify distribution y, is the probability of delta equals to 0, right? That's what it is. So therefore, and overall the x, that's what it is. So there's nothing to argue about. And if you go, many other authors have expressed the same kind of approach, and Mansky, for example, one of the ones earlier. So, and then, of course, the key thing is really, so, okay, now in different settings, how I might estimate these bounds. And more interestingly, can I introduce extra assumptions, extra sample assumptions or knowledges as a degree, right? Assumptions or knowledges. Sometimes you say for example, the one with higher income has lower probability to respond. Is it knowledge or is it assumption? You would say, okay, maybe somewhere in between, right? But something is, you say, okay. Anyway, do all these things you can bound. So I have actually, I don't think I can disagree with anything. So what should I discuss? So I say, okay, let's give you some other additional approaches to this type of problem to make you aware of. That's what there is. Okay, I agree with everything. Okay, so here's a very simple example: missing binary observations. So when delta equal to 1, you observe y either equal to 1 or 0. But when delta is equal to 0, you don't observe y, and so you have only 3 counts. The total, suppose something like this. And the green one, which is very thin, is the likelihood, the top is here, when you assume missing completely at random. Okay, if you make an assumption, strong assumption, missing completely at random, then you can point-wise identify the theta, and the likelihood will look very nice. But of course, if the assumption is wrong, then your point estimator will not converge to the truth, so you have bias. That's what it is. The red one is the profile likelihood of theta, coming from the trinomial distribution, because this is the trinomial sampling. This trinomial sampling distribution is identifiable, can be estimated. And you do the profiling, theta is related to those parameters, so you do the profiling of this likelihood, you get the profile likelihood of theta. And this profile likelihood will have a flat top in this case, which is essentially ranging from when all these y's, when delta equal to 0 are 0,
you get this point estimator. When all the given delta, all the y's are 1, you get this estimator. And between this, you cannot identify it. And the profile likelihood just exactly capture that. So this top is also sometimes called a likelihood ridge. Other authors have used these terms. So essentially, there is if you want to ask which points are most likely to be true, and given the data, you will say, actually, there's a bunch of them, and they're all equally likely to be true. But I can't really say one of them is a little bit more than. So the maximum likelihood, the idea is, will give you an interval rather than just a single point, okay? Unless you introduce some additional assumptions which are not supported in the data, like missing complete at random. Okay, the last function, the solid dot, what is it? This is called a corroboration function. And what is a corroboration function? Corroboration function is calculating under repeated trinomial sampling. What is the probability for a given theta value to fall into this ridge or this flat top? Okay, this again, the probability can be calculated. If you know the marginal distribution, you can calculate it exactly. If you don't know the marginal distribution of the trinomial, you can estimate it consistently and estimate this inconsistently. This is called the corroboration. And corroboration in this case, you see, the point is that all these points do not receive the same corroboration. That's the key thing. With likelihood, what are the most likely? There are a bunch of points receive equal strong support from data, but if you ask the question of corroboration, then not all the points actually have the same corroboration. So it brings another nuances into this. So what does this corroboration really mean? Okay, based on the trinomial, this is what we call minimal inference. Minimal in the sense that everything we do here only based on the observable trinomial sampling. We're not assuming anything in addition. Okay, this is something should be agreeable to all. If you don't agree to this, then we cannot discuss anything, right? That's what it is. Okay, so the marginal distribution of this trinomial can be identified, no problem, maximum. And this enables you to estimate consistently the true corroboration. The probability of this theta given values fall into such a region under repeated sampling. This can be calculated. You can do true level alpha set and so on. And given the estimated marginal distribution, you can calculate what we call the observed maximum corroboration. So this is the a chapter in the book Analysis of Integrated Data, which I did together with Ray Chambers. So these maximum points you can identify. So in this case here, just 1 point. It's not an interval. It's just 1 point. In this case, with this data, only 1 point receives the maximum corroboration. And what are these points that receive the maximum corroboration? So instead of the points are most likely to be true, these are the points hardest to refute. Okay. Okay, if you go to Karl Popper says you can refute something. If a scientific theory can be refuted, you know that? Scientific theory says prediction wrong, the scientific theory is refuted. That's the idea, right? Corroboration is a measure that the evidence, the data do not conclusively reject the hypothesis. So what is it doing? It is corroborating. It does not make the hypothesis true, but it is corroborating with the hypothesis. So the idea with corroboration is actually, instead of using likelihood to look for evidence in data in the sense that these are the values most likely to be true, you are using a function to look for evidence in data, which tells you what are the points hardest to refute. Is there any use? Yeah, there's some use, because basically it allows you to reject things. You cannot know which theta is the right one, but it can allow you conclusively to reject something with statistical accuracy. That's a point, okay? So you can build a corroboration test, for example. It is strongly Chernoff consistent. Basically, it means it has nice properties with respect to both type 1 and type 2 error, regardless of what the true theta value. Okay, that's something like that. So in this case, for example, with this data set, we can, this is the likelihood ridge, if you want, the parameter ridge. This is the 0.2. If you say the true marginal distribution probability of y equal to 1, I think maybe, what about the value 0.2? Well, the 0.2 value can be rejected with power 1 minus 0.018. And that power asymptotically converges to 1. So it's a very nice test. So you can reject this, even with this amount of observation. But the point in the middle receives very high corroboration, so it's hard to, it cannot be rejected, obviously. And even the point beside it, you cannot reject them at the level 0.05 or whatever, but obviously they are easier to reject than the point in the middle. That you see. Okay, that's my point, is drawing your attention to something other than the sort of the likelihood or uncertainty bound analysis in this kind of context. Okay. Second paper, I think it's very interesting because it is what I would call finite sample inference. So it does not rely on asymptotic arguments. The results I get holds for given population, given sample size. Okay, I don't need to resort to asymptotic arguments, which is nice because then you save a lot of trouble doing the asymptotic proofs, which can be hard, right? Okay, finite sample size, level alpha prediction interval, let's say the C, it should satisfy this condition. That is, the nominal level is alpha, and the coverage should be at least alpha. That's basically what it says. We are interested in finding this kind of intervals. That's the thing we want to look for. Okay. There are different ways of doing it from the conformal perspective. One is called full conformal. It is essentially using the so-called lemma of sample quantiles. Like Brunello was saying, this is the idee proof and so on. So essentially, it's a symmetry, basically. You can build functions f based on an augmented sample. The first n observations are really observed. The last one, x, you know, y is a stipulated value. What if this is the observation? And then you can put them together, build a function, and calculate how this y conformative to how close is to the rest. Does it look like the rest, or does it not look like the rest? If it look like the rest enough, then you include them in the interval. If it does not look like enough, then you reject them. That's the one. That's the procedure you repeat again. Of course, this is correct. This is because all you need is just symmetry. This function f, by the way, can be built from the sample. It doesn't need to be given in advance. If you give it in advance, obviously, but you don't need, because as long as this f is built on all these augmented sample, symmetry kicks in. So the results still hold. So the f can be sample built. It doesn't have to be given in advance. Okay? But the key problem is, of course, the computation. Basically, you need to try a lot of y values in order to get an interval for the next observation. And if you want to do for million observations, you have to repeat this million of times. So it's too much computation, basically. Okay. Split conformal. The split conformal says that I'm going to do a random partition of the observation I have into the training or the calibration they call, or other people call testing or whatever, right? So, and they do 50-50 because generally there's no theory telling what is the right split, okay? There's no, the theory is too hard. Nobody has the theory on this. What is the right split? 50-50 seems a reasonable balance, okay? Because you need the second set to build the interval. You need the first set to build a function that helps you to build the interval. Because if you don't build a function, you can just take the sample mean. But that is not efficient interval. You will not get an efficient interval. So that the function should be good. So therefore, you need some data to train that function. Otherwise, you lose efficiency. So therefore, what is the balance? Well, 50-50. I have no idea. So let's do 50-50. We do both jobs equally well, basically, essentially something like this. Okay, so 50-50 is probably a default choice. Although I'm sure in theory, for given data, given function you want to build, there will be a different split that is optimal. But it's just theory does not reach. We don't have the math to do that. Okay. So essentially, you build a model from the training sample S1. Now, given S1, that model becomes like given, God-given in advance. It's a constant for anything in S2. Right? So therefore, S2 has an exchangeability. So whatever the sample quantile lemma in S2 will allow you to do for the rest. So that's it. So this is simpler because you only do it once. You can build intervals for all the units outside. So you see, it saves the computing. You don't need to do it again and again. That's the whole point, right? So what I want to say is that actually, let me show you how this might be brought into a proper design-based framework, okay? Because what the reference Brunello mentioned essentially is arguing with replacement sampling, okay? And with replacement sampling is essentially IID, The only problem is that if you do with replacement sampling with unequal probability, then the distribution of the X in the sample and the distribution of the X out of the sample is different. That's the so-called covariate shift. But otherwise, it's still ID. So essentially, it's still ID. It's not really bring into the key thing, the sampling destroys the exchangeability is really due to without replacement sampling. Right? As long as you do with replacement sampling, it's not an issue. So we really need in theory, a general framework allows us to do without replacement, this type of setting. And this is called the design-based predictive inference framework. The paper is ready, available already online in JOS. It's a joint work with Luis Sanguel and Daniel Lee. Okay, so let me briefly explain what is the idea. First, what is predictive inference, design-based predictive inference? And secondly, how can we use that to do anything we want? Okay, what is design-based prediction? We always talk about model-based prediction, right? What is design-based prediction? Let's do some terminology. Okay, given the sample of observations, say you have yx associated with units 1 to m. You obtain the function, let's call it mu s. S is just designates the units that are in the sample. So S is the label of the unit. It's not the yx, right? S is just. The mu s just says that if you have a different set of units with their values, your function will be different. The mu s just emphasizes this, but it can be arbitrary, any function you can think of. Okay? That's the only thing it emphasizes. Prediction means that what I'm going to build this mu s for, you want to target something. So this mu s, if this something, this mu s build is target, is random, then you are interested in prediction. If this mu s you build for something that is considered as fixed, then you are in the estimation context. So that's the terminology. What is prediction? What is estimation? And then finally, what is design-based prediction is that when I do these things, the only thing random is the sample. All the yx are fixed. Okay, you have a finite population, whatever, yx fixed. The units you see, units you want to predict, all the yx are constant. The only thing varies is which unit is in your sample or not. That's the only thing. Now, if this sample variation is under probability design, then there is a PS. Okay? And if you do prediction within this framework, it's design-based prediction. Now, this sounds a little bit abstract, right? So what does it look like? I gave you a very specific example, very simple, right? Imagine a finite population, 4 units with these y values, 1, 2, 3, 6. Okay, it's a very simple population. I'm going to consider simple random sampling without replacement, sample size 2. Okay, so I listed out all the 6 possible samples. For each possible samples, I list out the sample mean, which is mu s, which is the function I'm going to build, okay? Just for illustration. That's the mu s I'm going to build, okay? And then for every sample, there is a corresponding out of sample y mean, okay? I'm also listing these 6 numbers. And then there's a set of all the 2 units that are out of sample. I'm listing that too, the y. The units that are out of sample. Given every sample, what are the units out of sample, right? And if I'm using the function to target those individual y's, what are the squared error? I'm listing that in the next block. This is the squared error. If I'm using mu s to target anything, these 2 values outside, these are squared error for the first one, this is squared for the, so this is all the squared error. And the sum of all these squared error, that's what I call dr, okay? Now, this is complete. You see everything, right? Now I'm telling you is that, think about it now. As the sample vary, as the sample one of these 6, all these quantities vary, right? Which units out sample vary. The out of sample mean of y vary. What are the individual values, the set of values that are out of sample vary. What about my dr using the function I do build from sample vary. So these are all random. Okay? So we are set up. We are set up for do design-based prediction now because we are using PS to target something that is random. So if we want to use any function, mu s, to target any of these quantities, we are doing design-based prediction. And what is design-based unbiased prediction? Well, because, for example, you know the sample mean and the out of sample mean and the simple random sampling without mean, they have the same expectation under the repeat sampling. So my sample mean is an unbiased predictor of the out of sample mean.
My sample mean is an unbiased estimator of the population mean fixed. But my sample mean is an unbiased predictor of the out of sample mean. Out of sample mean also varies as the sample varies. So this is called design-based prediction. Now the question is, can I predict the DR? Predict the YR bar is easy. What about the DR, the squared error? All this, can you do that? That is a new thing, okay? First concept, then what is the new? Okay, how do you do that? Design-based predictive inference. I'm going to target Y using a function called mu X, given X, an arbitrary model function. The mu can be anything you can think of. Can be linear regression, random forest, boosted, whatever, right? That's what you think about. Okay, first, there is a PQ design. So first, you select the sample, S, that's a probability sampling. And then how do you select the training sample? That's also a probability design. That's called the Q design. Given the sample, how do you select the training set? That's a Q design. So for example, K-fold partition, for example, simple random sampling out of S, or for example, bootstrap, whatever. All these are designs that's possible, common. Okay, how do you do that? Together, that's called the PQ design. The S is all the units that are not selected in the sample, but not selected in the training set, S1. That's S2. That's the test set. That's a holdout set. Okay, distinct. Now, the second element important is called subsampling Rao-Blackwell. So you build a function based on the training set S1. But that's only one training set, right? Under your design, if you do K-folding, if you do simple random sampling, you could do this again and again. So what is the expectation of your trained function on the training sample? That is called Rao-Blackwellization. That's mu bar is called, this function you built is called mu bar, and this is using all the sample units. Okay, so this is what is you are doing here. It's called Rao-Blackwellization because with respect to PS, S is a minimal sufficient statistic. And you are taking conditional expectation, conditioning on that, so you are doing Rao-Blackwellization. And again, you're doing this using a subsampling with respect to sampling, so therefore this is called subsampling Rao-Blackwellization. Okay, so this is the function. Now, given this mu bar, these errors, for example, the squared total error, that's the thing you are interested in if you're using the mu bar to do the population total estimation. This is the total squared error. This is what you're interested in if you're using the mu bar to do individual level prediction. Okay? Now, the paper shows you we can estimate all these things unbiasedly. Actually, we are predicting these things unbiasedly because STE and TSE both are random. As sample vary, both vary. But we can use the sample to build an unbiased prediction of this. And this is a finite sample result. It doesn't really matter which mu you give me. I don't need asymptotics. I don't need anything. This is always valid. Okay? This is called design-based predictive inference. Now, finally, sorry, I closed. Now I'm going to apply SRB to prediction, to intervals. Instead of capturing these errors, I can do SRB to intervals. Okay? The idea is very simple. Conditioning on the training sample, treat the test sample S2 as a sample from all the units out of this training sample. Okay, that's what it means, right? And there is a probability because this is a PQ design. The PQ design is known. You factorize reversely. There is a sampling design for S1 under the PQ design, and there's a conditional design of S given S1. So you have S, you have S2, no problem. Okay, so there's a probability, a conditional sampling probability for the units in the test sample selected from the rest out of the training set. There is a probability. In principle, it is there. Now, given that probability, you can, for example, estimate the population distribution of your errors because the mu S1 is built on the training sample. So everything you see is fixed now. So everything error you see in the test sample is just a constant. It's just a constant. When X1 is just constant. The only thing random is that you happen to these S2 error rather than the other S2 error. So we're reducing to finite population sampling, okay? So everything's straightforward. You have a probability sampling, you want to estimate the distribution, fine, go ahead, no problem. And once you do that, what we can do, once we estimate that finite population distribution of the errors, what we can do is we can now predict the coverage of any interval you give me that's built around mu S1. Okay, that's the point. any interval you build around μs1, I can now estimate the coverage because I know the distribution of all these errors around this one in the population. So you give me anything, for example, plus minus 2, you say. Mu for every outside of the unit, right? Mu x1, s, given x, I have a predictor, and then I plus minus 2. Just plus minus 2. Why not? Just plus minus 2. Okay? That's plus minus 2. So for every outside y, if you are in it, it's 1. If you are outside, it's 0. So this 0, 1, and completely depending on the error of the y to this mu x1. That's all there is. And because you know the distribution, you can calculate this average over all these 0, 1s. So that is the coverage of the interval you get. And that is a random variable as the S and S2 changes. Okay? So you are predicting this coverage, but you can do it unbiasedly, just like we do with these errors. So SRB PQ design is a completely general framework, allow you to do predictive inference. The only difference is that instead of doing predictive inference for predicting squared errors of various types, you can also do predictive inference for intervals if you're interested, or other things, so on. Okay? And the next step immediately we can do is to improve the split conformal is just a specific choice of how do you set these ZL, ZUs, right? And then this is just one split, right? This is one split, S1, S2. So you do route blackization to this again. So you apply route, so you do this again and again, you can estimate this coverage again and again. That will reduce the variance of this coverage estimator. So that will increase efficiency. So this split conformal, you do it once, but actually you can do it again and again and again under the same partitioning design. You partition 50-50. You partition 50-50 again, you get a different interval, right? You can take expectation of all these intervals. That is your route blackized, and that will be more efficient. It will have the same coverage, conditional coverage, therefore unconditional coverage remain the same, but the Monte Carlo error of the splitting is gone. So that is SRB. It will give you the increase of efficiency. Okay, thank you. I stop here. I'm sorry that I go on. We open for questions, sorry. Please.
To the question that is Brunero, you mentioned the problem of covariate shift, right? When you have unequal probability sampling, because as you mentioned, the marginal distribution of X in the sample is not the same as the marginal distribution in the population. And my question is, and this is a very naive question because I'm not very familiar with conformal prediction, but could we put the design variables in the model or the weights in the model and right, to correct for this informative sampling and then just apply just a regular conformal prediction? You see what I'm trying to say? Instead of the...
Yeah. You should be able to formalize in the probability distribution what are the steps of your design. If you are able to do that, why not? Yeah.
Thank you for your presentation. Elisabetta Carfagna, University of Bologna. I would like to ask a question to Professor Conti. Well, first of all, thank you very much for your talk. It's very interesting indeed. You tried to estimate an interval for the bias with respect to the mean square error. Did you think of trying to use this kind of estimate that you produce for trying to remove the bias of the estimate?
Unfortunately, this is not possible on the basis of the data. You can reduce the maximal bias provided you have information and not by taking a midpoint. You can produce a single estimate. The Lichung idea is very good and promising. You can produce a single estimate by a corroboration function. It should be studied in this problem, but it's a promising idea, very promising, because as he remarked, our model is partially specified in the language by Mansky, but we can't completely remove the bias. It's impossible because data don't have resolution enough. If you want to remove bias, you you have to, you need information on the process that generated data. Otherwise, and this is based on some assumption. For instance, the process corresponds in sampling theory to a sampling design which is non-informative. Then yes, otherwise you still have a bias, which is not removable, but you can evaluate the bias, or better, the maximal bias.
So I have a question for Brunero or Tulichun, because the discussion was of the same topic, and both of them really interesting. I didn't know anything about this kind of predictions, so now I have one more topic in my dictionary, in my statistical dictionary on my mind. This method, more or less, is something very similar, if I well understand, to what is typically used in machine learning, something like cross-validation. They leave one out or something like that. But I always had a question, I don't know if philosophical or practical, for me it's practical. I have 1,000 data, and they say you use 1/2 of them to estimate the model. Usually this is not in statistics a good idea, to use half of your data, not all the information that you have, to estimate the parameter of the model. And why I have to do it? Only to have a better estimate of the quality of prediction. What everybody does is estimate the quality of prediction with 1/2. But at the end, I use all the data to estimate the parameter. And this is not fine, because your quality is estimated on that sides, not on the full sides. I understand well or not?
You understood perfectly, but the question is the answer is as to I can answer in two different ways. The first one is that here the main goal is to have a prediction, not to estimate a model. So the problem is slightly different. And the second one is that you want to be completely non-parametric. And so the estimate that you are going to obtain can be improved using the second step. But let me say something in defense of the entire method. As Li Chung said, the real conformal idea use all the data, not just half. The problem is that if you use all the data at the first step, and then you want to compare the new data with the previous set, then you have to run again the model for each single value that you want to test whether to include or not in the this is crazy in a real application. So the idea starts from this approach, which make an optimal use of the data. If you want, as you correctly said, if you want to avoid the splitting, there is another approach that I didn't mention today, which is called Jackknife Plus, which is basically the same. And there is a recent paper on the annals by Candes, Barber, and others. And they avoid the splitting by using a different way to get the prediction interval. And this is based on a so-called Jackknife Plus, which is an improvement on Jackknife.
Okay, I can add a couple of things. So first, you remember I talk about you build a function on the training set.
But actually the function you want to use for all the out of sample units is to Rao-Blackwellize this function. So I don't just split once. You split many times. And this Rao-Blackwellized mu bar is using all the sample units now, because in the repetition, all the sample units can be gone into training, okay? So this obvious loss of efficiency of splitting sample is not the issue. Now, having said that, what is typical in the machine learning, sort of the mainstream or sort of the sort of on the street type of machine learning application is to say, I split my sample k-fold times. I use that result in the holdout sets to decide the tuning parameters or which model I'm finally going to use. And once I made this decision, I'm going to fit that model with dual tuning parameter to the full sample again. And that is the final predictor model I'm going to take to the out of sample units. That is actually what happens on the street, although it was not very obvious if you go to Hasty's book or something like that, okay? But that's what it actually happens. Now the question is to say, can you get error of that predictor? And that answer is important.